Hey everyone, welcome into lecture number 16 of linear algebra. This lecture is on eigenvalues and eigenvectors. So let's start by defining what an eigenvalue is and also an eigenvector. So for this, let's let A be a square matrix in Rn by n. And the following is going to be the definition of the eigenvalue. So a scalar, lambda. Lambda actually we'll see could be a complex scalar. So a scalar lambda is said to be an eigenvalue, or sometimes called a characteristic value of the matrix. So characteristic value of A if and only if, every definition is an if and only if, right? If and only if there exists a non-zero vector x, in this case, x, such that the following is true. Such that A times x is equal to that scalar, lambda, times x. Okay, so in other words, if the number then plays the same role, so basically the idea here is that if there's a non-zero vector such that multiplying the vector times the matrix, A times x, is the same as multiplying that vector by a number, lambda times x, then it's called an eigenvalue. The number is called an eigenvalue. All right, the vector itself in this scenario, the vector x, is called an eigenvector of A belonging to lambda. So this is called an eigenvector of A belonging to lambda. All right, so let's see how this works with a few examples. This is kind of an introductory lecture, so we're going to do mostly examples, and we'll talk about, some more important applications of eigenvalues and eigenvectors in future lectures. But for this one, let's just see. Let's say we're given a matrix A. In this case, the matrix is 4, -2 in the first row, 1, 1 in the second row, and a vector x, in this case, which we'll say is the vector 6, 3. I claim that this vector x is an eigenvector for the matrix A. So we can verify that by just multiplying these together and then try to factor out the lambda, try to see what the lambda is that corresponds to this, right? So if we multiply A times x, so this one I'm just kind of giving, we're given, right? We're given the vector, and we just want to observe. This is our first example, so that's why. And we multiply this out. Obviously, the product of a 2 by 2 matrix with a 2 by 1 vector is going to be another 2 by 1 vector. And when we work this out, this is going to be 24 minus 6. I'll just write out all the details, but 24 minus 6, and then 6 minus 3. So this is then going to be 18, 3 for the entries in this vector. This is 6 plus 3. 6 plus 3, and 6 plus 3 is 9, right? All right, and so then we claim that, or we're hoping to find that this is a scalar multiple of this vector up here. And notice we can factor a 9 out of both of these, a scalar 9, but that leaves us with a 2, 1. We want to be left with a 6 and a 3, right? So if we factor out a 3 from each of these, then we see, I'll write it again in 2 steps, 18 is 3 times 6, right? 9 is 3 times 3. We can factor out that scalar 3, and we're left with 3 times the original vector that we started with, 6, 3. And so we see 6, 3 here, 6, 3 here. And then our matrix A is behaving the same way as this number 3. It's like multiplying by the scalar 3. And so that tells us that, yes, this vector 6, 3 is an eigenvector of the matrix A. And not only is it an eigenvector, but the eigenvalue is 3, right? The eigenvalue that it corresponds to is 3. Or that it belongs to, by our definition, right, is 3. All right, so then the question becomes, in this example, we were just given the matrix and the vector, and then we just work it out, and you can kind of, just by inspection, see what the eigenvalue is. But for that, we had to know that we had this vector. We had to have this vector, 6, 3, right? Or a vector at least in the same direction as this vector, 6, 3, to be able to compute this way and find this eigenvalue 3. What if we don't know anything about the eigenvectors or the directions of the eigenvectors and we want to find an eigenvalue? So that raises a good question, right? So how do we find eigenvalues of a given square matrix? So the answer is in the definition, right? Our definition up here said that the eigenvalues are numbers, scalars, lambda, for which a times x is equal to lambda times x, right? So we look at this equation. So the defining equation is, again, a times x is equal to lambda times x. And in this scenario, a times x and lambda times x are both vectors in Rn, right? They're vectors in Rn. And so we can subtract the lambda, either one, but we can subtract the lambda x from both sides. And we can write this as a times x minus lambda times x should equal 0 now, right? The 0 vector in this case. And then we can try to factor out this vector x. But before we can do that, we have to insert a matrix product here because we're not just factoring out the vector x, we're factoring it out, it has to be factored out in a way that what's left is a legitimate mathematical object, right? A minus lambda doesn't make any sense. That's a matrix minus a number. So what we have to do is first insert an identity matrix here, right? Just replace x with I times x. That's perfectly legal. And at this point, now we can factor out the x's, and what's left is a difference of two n by n matrices. All right? So this factors to become a minus lambda I times the vector x equals the 0 vector. So this is yet another, so our definition, remember, of an eigenvalue was this, but everything we've done here has been an equivalence. So this is now another way to define an eigenvalue. An eigenvalue is a number, lambda, for which this difference, a minus lambda I, times a non-zero vector x is equal to 0. All right, and so we're going to use probably most of the time, unless we're given some information like in this previous example, most of the time we're probably going to use this equation to help us find our eigenvalues and then also our eigenvectors that correspond to those eigenvalues. All right, so basically what do we have to do? Well, we need to find the numbers lambda, the scalars lambda, which make this matrix a minus lambda I singular, right? So for which they have a non-trivial null space. We need to make sure that their null space has a non-zero vector in it, right? So let's write this out. I'm going to call this a theorem. It's not really a crazy theorem. It's just an equivalence of definitions, all right? So let's let A be an n by n matrix. The following are equivalent. And these are just going to give us different ways to think about eigenvalues. All right, so first of all, lambda, I'm just going to write this. So lambda is an eigenvalue. I'm going to start writing it as just E value, eigenvalue of A. So everything that I write after this is going to be an equivalent, essentially, definition, right, to the definition. So first of all, let's just write down, well, this is the definition. So I'm not going to rewrite this one, right? So ax equals lambda x. That's what I mean by this. Lambda is an eigenvalue of A. That was our definition. So everything else I write is going to be kind of new. The first thing, let's just write this equation, right? So A minus lambda I times x equals 0. But remember, this x has to be non-zero, right? So this has to be, we can say it this way. This equation has a non-trivial, non-zero solution. All right, so there's a non-zero solution to that equation. Another way to say this is, I said it out loud, we didn't write it, right? But another way to say this is that the null space of this matrix A minus lambda I is also non-trivial. It contains a non-zero vector, right? So the null space of A minus lambda I is non-trivial. It's not equal to the 0 vector. All right? That means then that the matrix A minus lambda I must be singular, right? If it has a non-trivial null space, then it's a singular matrix. So we can say that, right? A minus lambda I is singular. And then finally, if your matrix is singular, then what does that say about the determinant of your matrix? Well, it says that the determinant then of the matrix A minus lambda I must be 0. Okay, so actually the last one that I wrote here, this determinant of A minus lambda I equal to 0, that is going to lead us to probably the easiest way to compute the eigenvalues. So the easiest way to compute the eigenvalues. So let's do another example. So for this one, I want to compute the eigenvalues of this matrix A. Just do it 2 by 2 first. We're going to do a couple examples here. So 3, 2 in the first row, 3, negative 2 in the second row. So let's use this last item right here, item 5, and let's compute the eigenvalues this way. So the first thing we need to do is write down the matrix A minus lambda I. Well, what's that going to do? Lambda I is just a diagonal matrix with lambdas along the diagonal. So A minus lambda I is just going to be the matrix which looks pretty much like A, except it gets a minus lambda, right? So 3 minus lambda in the first component. 2 stays the same. 3 stays the same. Minus 2 minus lambda in this component. And then when we take the determinant, we can just do the formal determinant of this, right? So the determinant of A minus lambda I is then the product 3 minus lambda times negative 2 minus lambda minus 6, right? And we need to set this equal to 0. That's what the criteria is, that the determinant of this matrix is 0. And so at this point, I'm going to work this out a little bit more, and then we can write something down about it. But the minus can come out, so this can be written, we can take a minus out of each one, right? And so this can be written as lambda minus 3 times lambda plus 2 minus 6 should be 0. And then this equation then looks like lambda squared minus lambda minus 6 minus 6 equals 0. So this portion right here, I'm going to get a different color highlighter. But this right here, this is called the characteristic polynomial of the matrix. So this is a polynomial in lambda. P of lambda here is lambda squared minus lambda minus 12. This is called, again, the characteristic polynomial of A. Okay, so it's a characteristic polynomial of A. The determinant, so this is always going to be the characteristic polynomial, but now what do we need to do? We need to find the roots of the characteristic polynomial, right? The roots, or the zeros, those are what are going to be the eigenvalues, right? So this can now we can factor the whole thing, right? So now our P of lambda can be factored as what? Lambda minus 4 times lambda plus 3, right? And so this means that our eigenvalues are positive 4 and negative 3. These are our two eigenvalues. So these are the two numbers which make our matrix singular, our matrix A minus lambda I singular, right? Now what we need to do is find the corresponding eigenvectors. All right, so we need to find the corresponding eigenvectors. So this right here is the end of the answer for the eigenvalues. But let's remember how the eigenvectors work. Once we know the eigenvalues, then we can actually write out what our matrix is, right? So in this case, this one's going to be our matrix was 3 minus lambda, right? So 3 minus 4, 2 here, 3 here, and then negative 2 minus 4 in the last component. All right, and then we work this out, and we get negative 1, 3, 2, negative 6, and we need to find the null space of this, right? So we need to find the null space of A minus 4i. I wrote lambda here. I should have written 4 because we know for this example, for this portion of the work, the lambda is equal to 4. We need to find the null space of this. Well, how do we find the null space? We set this equal to 0. We can do an augmented matrix method. There's lots of different ways to do it, right? But notice that you cannot do an inverse matrix method because this is going to be a singular matrix. That's the whole point, right? This better be singular, and it is. So instead of doing, something like that, we can just write down an augmented matrix, and we can find the null space. So obviously these two equations, equation 2 or row 2 plus 3 times row 1 is going to cancel out, right? And then we can change the sign on this and write this as 1 minus 2, 0, 0, 0, 0. All right, and so then what does that mean? Well, notice that now there are infinitely many solutions, right, to this system. So we just need a basis. So eigenvectors are of the form, in this case we can say x2 is free, so we'll say alpha, and x1 is equal to 2 alpha, right? Let's just move this over, equal to 2 alpha. And so this means our eigenvectors for this corresponding to this eigenvalue lambda equal 4 are of the form alpha times 2, 1. All right, so any number alpha except for 0 will give us an eigenvector. All right, so of course that means alpha is not 0, but any other value of alpha gives us an eigenvector. And so actually what we end up with then is an entire vector space of eigenvectors if we include the 0 vector in that space, right? So the 0 itself is not an eigenvector, but every other vector in that vector space, that one-dimensional vector space, will be a vector, an eigenvector, corresponding to lambda equals 4. And that's called the eigenspace of this eigenvalue lambda equals 4. All right, so we'll write it this way. The eigenspace of lambda equals 4 is, and I'm kind of heuristically defining eigenspace here, but it's equal to the span of this basis eigenvector 2, 1. Okay, it's equal to the span of that. That's the eigenspace for the eigenvalue lambda equals 4. Okay, every vector in that space except for the 0 vector is an eigenvector that corresponds to this eigenvalue. All right, the other eigenvalue that we had for this one, we'll just do it all again. It works the same way, right? It was -3. And so same deal, the null space of a minus -3. So lambda a plus 3i, right? We'll do the null space in a second, but this matrix itself is going to be what? So it's going to be 3 plus 3, 2, 3, and then -2 plus 3. And so this one looks like 6, 3, 2, 1. Right? It's very similar. And so now we try to solve for the null space. So now we have the matrix 6, 3, 2, 1, augmented 0, 0. This one reduces to, we can just rearrange this, right? Just write 3, 1, 0, 0, 0, 0. And you know, this is not official row echelon form, but it's good enough to solve this, right? Because now what we can do is we can say, all right, let's let x1 be the free variable. Let's let this be alpha, right? And then x2 is equal to minus alpha. No, it's equal to -3 alpha, right? -3 alpha. All right, and this tells us that a basis for all of our eigenvalues in this case are equal to, or they're in the form alpha 1, -3. All right, and so the eigenspace for lambda equals -3 is given by the span of this basis vector here, 1, -3. And again, every vector except for the 0 vector itself is an eigenvector, right? Every vector in the span except for the 0 vector is an eigenvector that corresponds to the eigenvalue lambda equals -3. All right, let's do another example here. So for this one, I'm just going to compute the eigenvalues, but this is a 3 by 3 matrix. So we found the eigenvalues and the eigenspaces for that 2 by 2. But let's just find the eigenvalues for this matrix A. It's going to be a 3 by 3. 2, 1, 1 for the first column. -3, -2, -3 for the second column. 1, 1, 2 for the third column. All right. Remember, what we need to do is we need to first write down the matrix A minus lambda I. And it's just going to be 2 minus lambda, -3, 1. 1, -2 minus lambda, 1. 1, -3, 2 minus lambda. And then we need to compute its determinant, right? So determinant of A minus lambda I. Remember, this is what's called the characteristic polynomial. This determinant of a minus lambda I is a polynomial in lambda, right? It's a polynomial function in lambda, and it's given by, I'm just going to do my little cheat sheet method here to compute this determinant. But it's a determinant, so it's the same kind of product that we're used to, right? It's going to be this times this. Add those up, right? And then subtract these off. All right, so this one's going to be 2 minus lambda squared times negative 2 minus lambda. Then it's going to be plus a negative 3. So minus 3, plus another negative 3, so minus 3. And then it's going to be minus all these products, right? So this one's going to be negative 3 times 2 minus lambda. Another one that's exactly the same, negative 3 times 2 minus lambda. And then plus negative 2 minus lambda. And so now we just very carefully work all this out. So this one can be switched, right, to lambda minus 2 quantity squared. This one, a minus sign can come out, and then this will be written as lambda plus 2 minus 6 minus everything in here. So this is going to be negative 6 times 2 minus lambda minus 2 plus lambda. And then we just carefully work this all out. And so after working all this out, you'll get minus lambda cubed minus 2 lambda squared minus lambda. That's the characteristic polynomial. And now, of course, you want to set that equal to 0, right? So p of lambda equals 0 is the same as, you can factor out a lambda, a minus lambda, and then what's left? It's going to be lambda squared plus 2 lambda plus 1 equals 0, right? And so this means that lambda equals 0 and lambda equals negative 1 twice, actually, right? Because this is lambda plus 1 quantity squared, this term right here, lambda plus 1 quantity squared. And so this is a three-dimensional matrix, but it only has 2 eigenvalues, and this one is repeated twice, so lambda equals minus 1 happens twice. Now notice that this one, if lambda equals 0 is an eigenvalue, then this means that a minus 0 lambda, which is just a, is singular, right? So if your matrix is singular, then 0 is an eigenvector, sorry, an eigenvalue, and vice versa. Vice versa, right? So if lambda equals 0 is an eigenvalue, then your matrix must be singular. It must be singular. So the other two, the eigenspace, because the multiplicity of this eigenvalue is 2, the eigenspace of this one must be 2-dimensional, right? So, okay, so we'll leave that one there. So you should be able to find, in other words, 2 free variables when you solve the null space for lambda minus negative 1i. A minus negative 1i. So you should work that out as a recommended exercise. Just pause the video now and work out the eigenspace for lambda equals negative 1. All right, here's another example. So this is number 6 at this point. So number 6 is the following. Here's a matrix, still a 2 by 2 matrix, but A is equal to 1, 2 in the first row, negative 2, 1 in the second row. We want to find the eigenvalues of this. All right. So we do the same, all the same stuff, right? A minus lambda I is going to be our matrix. 1 minus lambda, 2, negative 2, 1 minus lambda. And then the determinant of this, which is our characteristic polynomial, p of lambda, which is determinant of A minus lambda I. This is going to be the product, 1 minus lambda quantity squared plus 4, and then this can be multiplied out to be lambda squared minus 2 lambda plus 1 plus 4, or lambda squared minus 2 lambda plus 5. And now remember, the eigenvalues are the roots of this polynomial, right? So they're the zeros of this polynomial, the roots of the equation p of lambda equals 0. And so that's what we have to solve. So lambda squared minus 2 lambda plus 5 equals 0. This can be solved by completing the square, right? Plus 4 equals negative 1. So lambda minus 2 quantity squared is negative 1. So this means that lambda is equal to 2 plus or minus I. The point here being that the eigenvalues can be complex, even though the matrix itself was not, right? So the matrix itself is real. It lives in the space R2 by 2, right? But R2 by 2 is a subspace of C2 by 2. So the eigenvalues are complex for this one. All right, and I'll leave this here, but the point is that it's definitely possible. We just saw it, right? It's possible to have complex eigenvalues. In that case, your eigenvectors, though, would have to also live in C2 by 1. So they have complex entries, right? So in this case, so if your eigenvalues are in the complex number system, then the eigenvectors must have at least one, but must have complex entries as well. And the reason for that is because there's going to be no way to multiply a number, which is complex, times a constant real vector and get back a real vector, right? That would make it complex. So your eigenvectors in this case must also have complex entries. And again, take a moment, pause the video, and work that out for yourself. Find the eigenspace of 2 plus I and the eigenspace of 2 minus I. You'll see that they're complex. They're complex vectors. All right, so I just have one more thing for this lecture, this introduction to eigenvalues and eigenvectors, eigenspaces. And this is the following. The sums and products of the eigenvalues are very important things, okay? So let's let A be an n by n matrix with, let's just say, with eigenvalues. So eigenvalues equal to, let's say, lambda 1, lambda 2, through lambda n. So there's always n eigenvalues if you count multiplicity, right? So some of these could possibly be repeats, right? Just like we saw up here. This one had negative 1 happen twice, but there's 3 total roots of this equation, right? Of this characteristic equation. So it's possibly repeating, right? So, well, no, that's not the right way to say it. Possibly with repeats. Possibly with repeats. So in other words, if you have an eigenvalue with a multiplicity greater than 1, you count each copy of that as a single eigenvalue in what I'm about to say now. It turns out that the determinant of A, of the matrix A, is always equal to the product of these eigenvalues. And it's going to be an exercise to work out the details of this in your homework, but the determinant of A is equal to the product of the eigenvalues, and then the trace of A, remember the trace is the sum of the diagonal elements of A. The trace of A is always equal to the sum of the eigenvalues. So the sum of the diagonal elements in your matrix always adds up to the sum of the eigenvalues, and the determinant of your matrix is always equal to the product of the eigenvalues. All right, now for a 2 by 2 matrix, let's see what this tells us then. So for A in our 2 by 2, what does that mean, right? Well, let's see. It turns out that our characteristic polynomial, in this case, is equal to lambda squared plus the trace of A times lambda plus the determinant of A. And it has to be this, okay? It has to be this because there's 2 roots, so it has to be lambda squared plus the sum, lambda 1 plus lambda 2 times lambda here, plus the product, lambda 1, lambda 2 here, right? And that's the only way that you can end up with lambda minus lambda 1 times lambda minus lambda 2. All right, so you add them up here. This is wrong. It's got to be minus the trace, right? Minus the trace. There, now it's right. Now it's right. Sorry about that. Yeah, so this is exactly right now. It tells us then that when we find our characteristic polynomial, I kind of work backwards from here, right? If you know you have lambda 1 and lambda 2 as your eigenvalues, then this must be your characteristic polynomial. And then you multiply these together to get this, right? And then you notice that, okay, this term right here is the trace, and this one is the determinant. But your characteristic polynomial then tells you both the trace and the determinant of your matrix. So let's do one final example here, and then we'll leave this introductory lecture and work. Hopefully, you guys work on some exercises here. But here's our matrix A. So A minus lambda I for this matrix is going to be the matrix 5 minus lambda, negative 18, 1, negative 1 minus lambda. And this means that the characteristic polynomial is given by 5 minus lambda times negative 1 minus lambda plus 18, right? And then we can just work this out. So this is going to be the same as, I always like to reverse this for, I don't know, simplicity of my mind, but now it's easier for me at least to look at. This is lambda squared minus 4 lambda minus 5 plus 18, or lambda squared minus 4 lambda plus 13. And so the claim then, if we believe what we said before, is that the trace should be 4 and the determinant should be 13, right? So the trace of A should be 4. The determinant of A should be 13. Let's check. Well, the trace, we can just see, the trace of this A is 5 minus 1. That is 4. So that's good. And the determinant of A, well, that's going to be negative 5, right, minus a negative 18, which is 13. So that's correct as well. And so it turns out that this always works, that the characteristic polynomial of a 2 by 2 matrix is the lambda squared minus the trace of A plus the determinant of A. All right? So, like I said, this is just a brief, quick introduction to eigenvalues, eigenvectors, eigenspaces of square matrices. We will study these in depth in the next few lectures. And for now, though, I'm going to leave this, and I'll talk to you guys in the next one.